This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recorded by Annie Coleman. www.anniecoleman.com. Relativity. The Special and General Theory by Albert Einstein. Continuing Part 2. Sections 21 through 23. Section 21. In what respects are the foundations of classical mechanics and of the special theory of relativity unsatisfactory? We have already stated several times that classical mechanics starts out from the following law. Material particles sufficiently far removed from other material particles continue to move uniformly in a straight line, or continue in a state of rest. We have also repeatedly emphasized that this fundamental law can only be valid for bodies of reference K which possess certain unique states of motion, and which are in uniform translational motion relative to each other. Relative to other reference bodies, K the law is not valid. Both in classical mechanics and in the special theory of relativity, we therefore differentiate between reference bodies K, relative to which the recognized laws of nature can be said to hold, and reference bodies K, relative to which these laws do not hold. But no person whose mode of thought is logical can rest satisfied with this condition of things. He asks, how does it come that certain reference bodies, or their states of motion, are given priority over other reference bodies or their states of motion? What is the reason for this preference? In order to show clearly what I mean by this question, I shall make use of a comparison. I am standing in front of a gas range. Standing alongside of each other on the range are two pans, so much alike that one may be mistaken for the other. Both are half full of water. I notice that steam is being emitted continuously from one pan, but not from the other. I am surprised at this, even if I have never seen either a gas range or a pan before. But if I now notice a luminous something of bluish color under the first pan, but not under the other, I cease to be astonished, even if I have never before seen a gas flame. For I can only say that this bluish something will cause the emission of the steam, or at least possibly it may do so. If, however, I notice the bluish something in neither case, and if I observe that the one continuously emits steam whilst the other does not, then I shall remain astonished and dissatisfied until I have discovered some circumstance to which I can attribute the different behavior of the two pans. Analogously, I seek in vain for a real something in classical mechanics or in the special theory of relativity, to which I can attribute the different behavior of bodies considered with respect to the reference systems K and K prime. Begin footnote. The objection is of importance more especially when the state of motion of the reference body is of such a nature that it does not require any external agency for its maintenance. For example, in the case when the reference body is rotating uniformly. End footnote. Newton saw this objection and attempted to invalidate it, but without success. But E. Mach recognized it most clearly of all, and because of this objection, he claimed that mechanics must be placed on a new basis. It can only be got rid of by means of a physics which is conformable to the general principle of relativity, since the equations of such a theory hold for every body of reference, whatever may be its state of motion. Section 22. A few inferences from the general principle of relativity. The considerations of Section 20 show that the general principle of relativity puts us in a position to derive properties of the gravitational field in a purely theoretical manner. Let us suppose, for instance, that we know the space-time course for any natural process whatsoever, as regards the manner in which it takes place in the Galilean domain relative to a Galilean body of reference K. By means of purely theoretical operations, i.e., simply by calculation, we are then able to find how this known natural process appears as seen from a reference body K', which is accelerated relatively to K. But, since a gravitational field exists with respect to this new body of reference K', our consideration also teaches us how the gravitational field influences the process studied. For example, we learn that a body which is in a state of uniform rectilinear motion with respect to K, in accordance with the law of Galilei, is executing an accelerated and, in general, curvilinear motion with respect to the accelerated reference body K', chest. This acceleration, or curvature, corresponds to the influence on the moving body of the gravitational field prevailing relatively to K'. It is known that a gravitational field influences the movement of bodies in this way, so that our consideration supplies us with nothing essentially new. However, we obtain a new result of fundamental importance when we carry out the analogous consideration for a ray of light. With respect to the Galilean reference body K, such a ray of light is transmitted rectilinearly with the velocity c. It can easily be shown that the path of the same ray of light is no longer a straight line when we consider it with reference to the accelerated chest, reference body K'. From this, we conclude that, in general, rays of light are propagated curvilinearly in gravitational fields. In two respects, this result is of great importance. In the first place, it can be compared with the reality. Although a detailed examination of the question shows that the curvature of light rays required by the general theory of relativity is only exceedingly small for the gravitational fields at our disposal in practice, its estimated magnitude for light rays passing the sun at grazing incidence is nevertheless 1.7 seconds of arc. This ought to manifest itself in the following way. As seen from the Earth, certain fixed stars appear to be in the neighborhood of the sun, and are thus capable of observation during a total eclipse of the sun. At such times these stars ought to appear to be displaced outwards from the sun by an amount indicated above, as compared with their apparent position in the sky when the sun is situated at another part of the heavens. The examination of the correctness or otherwise of this deduction is a problem of the greatest importance, the early solution of which is to be expected of astronomers. Begin footnote. By means of the star photographs of two expeditions equipped by a joint committee of the Royal and Royal Astronomical Societies, the existence of the deflection of light demanded by theory was first confirmed during the solar eclipse of 29th May, 1919. End footnote. In the second place, our result shows that, according to the general theory of relativity, the law of the constancy of the velocity of light in vacuo, which constitutes one of the two fundamental assumptions in the special theory of relativity, and to which we have already frequently referred, cannot claim any unlimited validity. A curvature of rays of light can only take place when the velocity of propagation of light varies with position. Now, we might think that as a consequence of this, the special theory of relativity, and with it the whole theory of relativity, would be laid in the dust. But in reality this is not the case. We can only conclude that the special theory of relativity cannot claim an unlimited domain of validity. Its results hold only so long as we are able to disregard the influences of gravitational fields on the phenomena, for example, of light. Since it has often been contended by opponents of the theory of relativity that the special theory of relativity is overthrown by the general theory of relativity, it is perhaps advisable to make the facts of the case clearer by means of an appropriate comparison. Before the development of electrodynamics, the laws of electrostatics were looked upon as the laws of electricity. At the present time we know that electric fields can be derived correctly from electrostatic considerations only for the case, which is never strictly realized, in which the electrical masses are quite at rest relatively to each other and to the coordinate system. Should we be justified in saying that for this reason electrostatics is overthrown by the field equations of Maxwell in electrodynamics? Not in the least. Electrostatics is contained in electrodynamics as a limiting case. The laws of the latter lead directly to those of the former, for the case in which the fields are invariable with regard to time. No fairer destiny could be allotted to any physical theory than that it should of itself point out the way to the introduction of a more comprehensive theory in which it lives on as a limiting case. In the example of the transmission of light just dealt with, we have seen that the general theory of relativity enables us to derive theoretically the influence of a gravitational field on the course of natural processes, the laws of which are already known when a gravitational field is absent. But the most attractive problem, to the solution of which the general theory of relativity supplies the key, concerns the investigation of the laws satisfied by the gravitational field itself. Let us consider this for a moment. We are acquainted with space-time domains which behave approximately in a Galilean fashion under suitable choice of reference body, i.e., domains in which gravitational fields are absent. If we now refer such a domain to a reference body K' possessing any kind of motion, then relative to K', there exists a gravitational field which is variable with respect to space and time. Begin footnote. This follows from a generalization of the discussion in section 20. End footnote. The character of this field will of course depend on the motion chosen for K'. According to the general theory of relativity, the general law of the gravitational field must be satisfied for all gravitational fields obtainable in this way. Even though by no means all gravitational fields can be produced in this way, yet we may entertain the hope that the general law of gravitation will be derivable from such gravitational fields of a special kind. This hope has been realized in the most beautiful manner, but between the clear vision of this goal and its actual realization, it was necessary to surmount a serious difficulty, and as this lies deep at the root of things, I dare not withhold it from the reader. We require to extend our ideas of the space-time continuum still farther. Section 23. Behavior of clocks and measuring rods on a rotating body of reference. Hitherto I have purposefully refrained from speaking about the physical interpretation of space and time data in the case of this general theory of relativity. As a consequence, I am guilty of a certain slovenliness of treatment, which, as we know from the special theory of relativity, is far from being unimportant and pardonable. It is now high time that we remedy this defect, but I would mention at the outset that this matter lays no small claims on the patience and on the power of abstraction of the reader. We start off again from quite special cases, which we have frequently used before. Let us consider a space-time domain in which no gravitational field exists relative to a reference body K, whose state of motion has been suitably chosen. K is then a Galilean reference body as regards the domain considered, and the results of the special theory of relativity hold relative to K. Let us suppose the same domain referred to a second body of reference, K', which is rotating uniformly with respect to K. In order to fix our ideas, we shall imagine K' to be in the form of a plane circular disk, which rotates uniformly in its own plane about its center. An observer who is sitting eccentrically on the disk K' is sensible of a force which acts outward in a radial direction, and which would be interpreted as an effect of inertia, centrifugal force, by an observer who was at rest with respect to the original reference body K. But the observer on the disk may regard his disk as a reference body which is at rest. On the basis of the general principle of relativity, he is justified in doing this. The force acting on himself, and in fact on all other bodies which are at rest relative to the disk, he regards as the effect of a gravitational field. Nevertheless, the space distribution of this gravitational field is of a kind that would not be possible on Newton's theory of gravitation. Begin footnote. The field disappears at the center of the disk and increases proportionally to the distance from the center as we proceed outwards. End footnote. But since the observer believes in the general theory of relativity, this does not disturb him. He is quite in the right when he believes that a general law of gravitation can be formulated, a law which not only explains the motion of the stars correctly, but also the field of force experienced by himself. The observer performs experiments on his circular disk with clocks and measuring rods. In doing so, it is his intention to arrive at exact definitions for the significance of time and space data with reference to the circular disk K', these definitions being based on his observations. What will be his experience in this enterprise? To start with, he places one of two identically constructed clocks at the center of the circular disk, and the other on the edge of the disk, so that they are at rest relative to it. We now ask ourselves whether both clocks go at the same rate, from the standpoint of the non-rotating Galilean reference body K. As judged from this body, the clock at the center of the disk has no velocity, whereas the clock at the edge of the disk is in motion relative to K in consequence of the rotation. According to a result obtained in section 12, it follows that the latter clock goes at a rate permanently slower than that of the clock at the center of the circular disk, i.e., as observed from K. It is obvious that the same effect would be noted by an observer whom we will imagine sitting alongside his clock at the center of the circular disk. Thus, on our circular disk, or to make the case more general, in every gravitational field, a clock will go more quickly or less quickly according to the position in which the clock is situated, at rest. For this reason, it is not possible to obtain a reasonable definition of time with the aid of clocks, which are arranged at rest with respect to the body of reference. A similar difficulty presents itself when we attempt to apply our earlier definition of simultaneity in such a case, but I do not wish to go any farther into this question. Moreover, at this stage, the definition of the space coordinates also presents insurmountable difficulties. If the observer applies his standard measuring rod, a rod which is short as compared with the radius of the disk, tangentially to the edge of the disk, then, as judged from the Galilean system, the length of this rod will be less than I, since, according to section 12, moving bodies suffer a shortening in the direction of the motion. On the other hand, the measuring rod will not experience a shortening in length as judged from K, if it is applied to the disk in the direction of the radius. If then the observer first measures the circumference of the disk with his measuring rod, and then the diameter of the disk, on dividing the one by the other, he will not obtain as quotient the familiar number pi equals 3.14, etc., but a larger number. Begin footnote. Throughout this consideration, we have to use the Galilean non-rotating system K as reference body, since we may only assume the validity of the results of the special theory of relativity relative to K. Relative to K', a gravitational field prevails. End footnote. But a larger number, whereas, of course, for a disk which is at rest with respect to K, this operation would yield pi exactly. This proves that the propositions of Euclidean geometry cannot hold exactly on the rotating disk, nor in general in a gravitational field, at least if we attribute the length I to the rod in all positions in every orientation. Hence the idea of a straight line also loses its meaning. We are therefore not in a position to define exactly the coordinates x, y, z relative to the disk by means of the method used in discussing the special theory, and as long as the coordinates and times of events have not been defined, we cannot assign an exact meaning to the natural laws in which these occur. Thus, all our previous conclusions based on general relativity would appear to be called in question. In reality, we must make a subtle detour in order to be able to apply the postulate of general relativity exactly. I shall prepare the reader for this in the following paragraphs. End of sections 21 to 23. Read by Annie Coleman in St. Louis, Missouri, on August 13th, 2006.